So next we are going to review conditional probability. So what is a conditional probability and how it's different from normal probability? So let's go back to the previous example of throwing a dice. We're taking a cup and putting a dice in a cup and we're shaking it. And then we are putting it on the table. So basically our dice is under the cup and we don't know what is the outcome. So we want to know the probability of event A, and event A in this case will be rolling a 6. So we want to know what is the probability for us to getting a 6. If we have a conditional probability, the game is now changed so that we have a neutral observer who is allowed to look at the result. However, the observer doesn't tell us the result, unfortunately, but he gave us a hint. He told us that the even number was rolled. So before we had only event information, but in conditional probability, we have another piece of information. So how does information change the estimate of the probability of having rolled a number 6? So the extra information that we get an even number is corresponds to the event B. So if event A was rolling 6, then event B is rolling an even number. This information allows the sample set omega to be constrained only by outcomes that exist in event B. So this is standard one. And this is our conditional with B. Because we know that this, and this are not valid. And this event constrains our sample set omega. How we write it down? Rolling 6 if we know that the number is even number. So we write it as following. We write it probability of A given B. So this one we read it as given. The main event is always in front because we want to know what is the probability of 6. And the extra information comes after the slash. So this case will be what is probability A given B. We can again try to draw Venn diagram somewhere over here, event A and event B. And this is omega. So this is a standard drawing that we saw, but for our particular example, our Venn diagram will look a bit different. We know that A is a subset of B, and in this case it will look a little bit different. So it will look like this. So we have event B here, and A and B. So here is 6, and here is 2 and 4. So what is the probability of A given B? So we're interested in this area here. Probability of event A given B will be equal to probability of A and B divided to probability of B. I think if we look at this picture here, it becomes clear why. So then we know that probability of A and B is probability of getting 6. And probability of getting 6 is 1/6. And we divide it to probability of getting B or probability of getting even number. We solved it before and we know that it's 3/6. And finally, we're getting the probability of event A given B is equal to 1/3. So this is the rule of conditional probability. Next topic that we want to cover today is very important and very cool one. It's Bayes' rule. I want to make a small remark that probability of A and B is the same as B and A. The intersection of A and B is the same as intersection of B and A. This is the same, so we can write them and interchange them. So in the previous slide, we saw a formula of probability of event A given B is equal to probability of event A and B divided the probability of event B. And correspondingly, if we want to find the probability of event B given A, is probability of B and A divided the probability of A. And we know also, so this and this are basically the same. Okay, and we can rewrite this equation for probability of B and A. If we rewrite it, then we will see that in order to find this piece of information, we need to multiply probability of B given A to probability of A. Thus, if we rewrite the main formula here, by replacing this with this one, we'll get probability of A given B. So we put this one here. So it's probability B given A multiplied the probability of A and divided the probability of event B. So this is the Bayes rule. Why do we need it? It's helpful because sometimes in some situations it's easier to calculate probability B given A than finding probability A and B. Depending on the situation, if you know one of those, you can use the Bayes rule to find another one. So let's take the previous example and calculate probability of A given B. And we remember that A was getting 6 and B was getting an even number, 4 and 6. So using Bayes rule, why we're using Bayes rule? Sometimes it's very tricky to calculate this piece of information directly. And probability of B given A is easier to find. Let's look at probability B given A. It means that we want to find probability of getting odd number if we know that the final number is 6. It means that it's certain event, so we're getting odd number definitely. And that's why probability of this event will equal to 1. And if we know that probability of getting A or 6 is 1/6 and getting the odd number is 3 divided to 6. And again, we're getting the same answer as we had on the previous slide when we described conditional probability. So it means that depending on situation and looking at different individual example, you can decide whether you want to use Bayes rule or you want to use the formula for conditional probability. Okay. Next, we're going to cover independence of events. If we have two events, if we have two completely independent events that happening one first and the second one, and they're kind of not related to each other, then finding probability will be a little bit different. So, for example, if we have A and B completely independent events, so for example, we have two dices and we are throwing them one separately and another one also separately. So, and we are not interested on the simultaneous result. We're throwing first dice and then we're throwing the second dice independently. And in this case, probability of A given B will just equal to probability of A because B will not make any influence on event A, because they are independent. So if we write the rule for conditional probability that we had before, and we know that this here is probability of A, and if we want to rewrite the formula for this part, so probability of A and B happening will be equal to probability of A multiplied to probability of B. So let's have an example. Rolling 2 dice. First event will be that first dice is 5. And event B is second dice is 3. So A and B here will be 5 and 3. And the probability of getting A and B will be 1/6 multiplied to 1/6, and we get 1/36. So this was probability when we have independent events. That's it for today, and I hope the videos for today were quite helpful for you. If you have more questions or would like to have additional videos, feel free to leave it in our feedback section, and see you in the next chapter.